I'm going to do a couple of questions here just to help you if you're trying to figure out how does the Pythagorean theorem connect with what we've been looking at in terms of polygons. Really, the Pythagorean theorem pops up a lot if there are questions where you're trying to figure out what the apothem is and you don't already know it. And if you remember the Pythagorean theorem, you remember that it's really only something that works when you're trying to deal with right-angled triangles. So you need to first figure out where in the question the right angled triangle is showing up. If you look at this one here, this question is telling you you've got a regular hexagon inscribed in a circle. If the radius of the circle is 9 centimeters and the area of the hexagon is 210.44, what's the length of the apothem? So you might look at this and say, well, to be honest, I don't see any right angled triangles. I mean, I see a 90-degree angle here, but it's just going up into space here. I don't see any triangle. Well, in this case, you actually are dealing with a triangle. I'm going to, let's see, what's an effective way of doing this? I'm going to just zoom in. Let's do a very poor construction of this diagram. I'm going to redo it here. So let's say you've got a circle here, which we're going to make a nice shiny color like green. And then you've also got inside it this hexagon, which I'm going to do a terrible job of drawing here. This hexagon is meant to be a regular hexagon. It's not going to be because I'm doing it a little too shabbily for that to work. But if you look at this picture here and you say, let me assume that what I'm trying to do here is have all these corners of what is intended to be a regular hexagon on the edge of this circle. And I've got, again, this dotted line, which is your apothem. You notice your apothem going down to one side, making a 90-degree angle down here. Even though there's no right angle triangle showing up, when it tells you the radius of the circle is 9 centimeters, that means from here down to the edge of the circle is 9 centimeters. But more importantly, it means from here, if I go to this edge of the circle, it's going to be 9 centimeters as well. And the reason why I say that's more important is because suddenly that is what's actually giving me a right angled triangle. When you see a right-angled triangle, that's your passport to Pythagorean ness, which is not a word, but I'm going to say it today. So we have a right-angled triangle, and the thing with right-angled triangles is if you know two sides of it, either the two short sides, the two legs, that's the two sides that touch the 90-degree angle, or one of the short sides and the hypotenuse, which is the nice long side here, the diagonal-looking one that doesn't touch 90 degrees, you can always find the third one. In this case here, if I want to do that, I just have to make sure, since the apothem's missing, that I know how long this side is and how long this side is. This side here, the hypotenuse, since it's the radius of your hexagon, since it's the radius of the circle that is going around the corners of the hexagon, that radius, 9 centimeters, is also the length of the hypotenuse. So you can already write that in. And you've got 9 centimeters here as the length of this guy. And you might say, well, this thing doesn't tell me the perimeter or anything. How am I supposed to know how long this side length is? You wouldn't know, except you're dealing with a hexagon. So whenever you're dealing with a hexagon, it's like this amazing shape that has all these interesting properties. And one of the things about it is that if you divide a hexagon up into triangles, the way we often do with regular polygons when we're thinking about finding their area, if you divide it up like this, then if this were a perfect drawing, which again it's not, all of these would be equilateral triangles, which means if this radius is 9 and this is also one side of the equilateral triangle, then this other side is 9 centimeters. And that third side, which is down at the bottom of the triangle down here, is also 9 centimeters, right? And that happens to be the side length of my hexagon as well. See this equilateral triangle here? 9 centimeters all the way around. So now we know if this whole side length is 9 centimeters, then if we zoom in on that triangle there, half of a side is going to be this bottom of the triangle. That right there is going to be 4.5 centimeters in this question. So now we have a right angle triangle. We know the hypotenuse is 9. We know that one of the legs is 4.5 centimeters. And so now we can do a calculation where let me show you what it would look like. You would calculate, okay, let me write it out for you. It can be confusing. People make mistakes here. So your Pythagorean theorem, it's a squared, I can't do exponents on this, plus b squared equals c squared. Right? That's your basic Pythagorean theorem. And you always got to figure out what numbers go in where. Here, the number I'm missing, I'm going to use A for it because it's the apothem. That's one of the legs, right? This 4.5, that's also one of the legs. I'm going to use that to go in B here. And 9 centimeters is the hypotenuse, so that should go in C. So what you have now is A squared plus 4.5 squared plus your hypotenuse squared, which is 9 is your hypotenuse. Oh, sorry, equals your hypotenuse squared. So that is now your equation. And now you just got to calculate it, right? You do 9 squared to get 81. So I've got A squared plus 4.5 squared, which is 20.25 in your calculator. And then 9 squared gives you 81. So A squared plus 20.25 gives you 81. Now to get just A, I'm going to have to subtract 20.25 from both sides. Let me do that. I'm subtracting 20.25 from both sides, and that leaves me with just A squared on the left, which is what I want. And on the right, what I have is 81 minus 20.25, which is 60.75, I think. Yeah, that looks right. So A squared equals 60.75. And if you want to find out what A is, you just take your 60.75, and then you square root it to find out what that is, 7.79. So that means that A is 7.79 centimeters. Oops, what am I doing here? A equals 7.79 centimeters. And that means you found your apothem using the Pythagorean theorem. This question is just asking you to find the apothem. There's nothing else you need to do, and there you have it. And I think that, oh yeah, I said I'd do a second one. How much time do I have here? Been going on for a while. All right, so this one's a little different. It tells you the radius of the circle again. So let me just erase this here. In this pentagon, you've got the radius of the circle is 10 centimeters. And you've got a, let me draw this pentagon in here. You've got what's supposed to be a regular pentagon inscribed inside this circle, like this. Not a perfect pentagon, but you get the idea. And the radius of the circle is 10 centimeters. So that means from here, the center of the polygon, to this corner here, I know that that is 10 centimeters. And each side of the pentagon is 11.76. Find the area of the pentagon. So I'm going to put that each side is 11.76 centimeters. That means I know down here this is 11.76. So in this one here, you see if you look at this diagram here, it's trying to give us a hint. It's trying to tell us, okay, you probably want to think about this apothem here, which is the distance from the center down to the middle of one side. I'm going to put a little letter A there. And in order to calculate area, the formula we know, it's number of sides times the side length times the apothem divided by 2. So if we can just get the apothem for this, we'll be able to calculate the area. And the way you do that is you would figure out, okay, this whole side is 11.76. If I can get half of that, which would be 5.88, I'm guessing. Let's just go with that, 5.88 centimeters. That's now 1/2 of the side length. And that's going to be useful because even though I didn't draw it very well, this is a right angle triangle. I've got my hypotenuse of 10, one leg of 5.88, and the missing leg is also my apothem, which is what I want in order to get the area here. So you would, let's make it colors we can see, you would write A squared plus B squared equals C squared, and then you would say, okay, well, A squared, I'm going to make my apothem A. I'm going to make B be this leg here, 5.88, which I've got a square, and I make it equal to the hypotenuse squared. The hypotenuse is 10, so they're equal to 10 squared. So that's your equation that you're working on. A is your apothem. That's one of the two legs in the Pythagorean theorem. 5.88 is your other leg. And then 10 is your hypotenuse. So a squared plus b squared equals c squared. Then I don't know what 5.88 squared is off the top of my head. Let's look at that. 5.88 squared. 34.5744. Just 34.57 for now. So I've got a squared. Oops, what am I doing? There we go. A squared plus 37.54. Did I get that right? 34.57. Glad I checked. 34.57 equals 10 squared, which is just 100. So that's your next line here. And now to solve for a, you're going to subtract 34.57 from both sides. And when you do that, what happens is you have a squared is equal to 65. What was the thing here? 34.5 cents. So 65.43. 65.43. And now to find out what a is, I just have to square root 65.43. And once I do that, I'll have my apothem, 8.09, if I'm rounding it properly. So a is roughly equal to 8.09 centimeters. And once you have your apothem here, you've done all the hard work doing the Pythagorean theorem. Now it's just a matter of using the area formula. You do number of sides, which is 5, times the side length, which is 11.76, times the apothem, 8.09, divided by 2, and that'll give you your area.